Well, comparing gases can be difficult because there are so many parameters, so many variables. And so one thing we use to make that a little easier is something called standard temperature and pressure. Standard temperature and pressure, abbreviated STP. So standard pressure is 1 atmosphere, which is the same as 760 torr. That's like normal pressure, right? An atmosphere. Standard temperature is going to be 273 Kelvin or 0 degrees Celsius. Now that's not room temperature. That's the temperature that water freezes and melts at. So that's an easy temperature to work with because you can put whatever container of gas you're dealing with in a bath of ice water and you can know that it's going to be at 0 degrees Celsius. So STP is useful for making comparisons between gases. There's another thing that we talk about called the molar volume of a gas. So molar mass was the mass of a mole. Molar volume is the volume of a mole. But we have to specify temperature and pressure. So molar volume is the volume occupied by 1 mole of gas at STP. So we could calculate that. Let's do that. So here we're looking for the greatest volume. So am I looking for the sample with the fewest particles or the most particles? Which will take up more space? More particles of gas, right? So I'm looking for the sample that has more particles. They all have the same mass. So am I looking for the heaviest or the lightest? So let's just think about this. So here's a 10-pound box, and here's a 10-pound box. And this one has ping pong balls, and this one has bowling balls. Which box has more balls in it? The ping pong balls, right? Because this probably only has 1 bowling ball. 1 10-pound bowling ball, that would be the 10 pounds. Here, ping pong balls weigh like next to nothing, right? So this box is going to have lots and lots of ping pong balls. Why? Well, because each ping pong ball weighs less. So here, if we're trying to find out which one has more particles, we're looking for the one that each particle weighs the least. So is that going to be hydrogen, oxygen, or argon? Hydrogen. So this one, 1 gram of hydrogen will take up more space than 1 gram of oxygen or 1 gram of argon. Any questions? I see disbelief. Let's do a calculation and I'll prove it to you. So 1 gram of hydrogen. So I can convert this to moles. And then I can convert this is at STP, and convert this to liters. So 1 gram divided by 2.016 times 22.4. 11.1 liters. Let's just do the oxygen. 1 gram of O2. 1 mole of O2 weighs 32 grams. And 1 mole will take up 22.4 liters. The same mass will have a different volume. If the volumes are the same, the number of moles of gas are the same, but not the mass. So this is one of those questions that we hope that you can solve without doing a calculation. It's conceptual. Do you understand the concepts, right? But some of these problems, if you're less like one of those people that, I don't like concepts, I just want to calculate a number. Well, you could do a calculation for a lot of these and figure out what the answer was. It just might take a little bit longer. Density. So gas density is going to vary depending on the pressure and the temperature. So we learned earlier that density is the ratio of the mass of something to its volume. Densities for gases are usually given in grams per liter instead of grams per milliliter because they occupy so much more volume and they are so much less dense that grams per liter gives us a nicer density. So your book gives you a formula so that you can calculate the density. And that works and that's nice, but that's another formula to remember, another equation to remember. So I'm not going to show you that. We know that density is the mass divided by the volume. So what we can do to calculate density is we can assume a 1 mole sample. The density does not change depending on how much of the gas you have. Density is one of those intensive properties. So if we say we have a mole, then the mass of this is going to be the molar mass of the gas, right? So we can find the mass of 1 mole, and the density is going to be the volume of 1 mole. Well, at STP, that's 22.4, right? So here we're going to calculate the densities of helium and nitrogen gas. So the density for helium will be the mass of 1 mole, 4.003 grams, divided by the volume of 1 mole, which is 22.4 liters. .003 divided by 22.4, 0.179 grams per liter. Calculating the density of nitrogen, these are elements by themselves, and so we do have to ask ourselves, is this a diatomic element? And nitrogen is. So the molar mass of 1 mole, the mass of 1 mole is going to be 2 times 14, or 28.02 grams, because it's N2. So that's the mass of 1 mole divided by the volume of 1 mole. .25 grams per liter. So same conditions, standard temperature and pressure. Bless you. If we have the same number of moles, we're going to have the same volume also, but the density will not be the same because the mass of those particles is different. Any questions? Well, what if we are calculating density under other conditions? It's the same idea, it's just going to take a few more steps. So this is that equation that the book gives you. Density is the pressure times the molar mass divided by RT. Again, that works, but you have to remember it. So I think it's better to take things that we are having to remember anyway, like the density equation. Density is mass over volume. So we can find the volume using the gas law. And if there's not a quantity given, we're just going to choose 1 mole of gas. Sometimes it'll tell you what the quantity is, and then you've just got that. Let's do an example of this. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So, highlight the numbers, highlight the question. We want the density. Take those numbers and write them down. 742 millimeters of mercury, 45 degrees Celsius. So this first one is the pressure, and the second one is the temperature. So we did that, and then we're like, that doesn't look like enough. Doesn't look like enough info, does it? Well, that's looking at the beginning of the problem. Let's try looking at it from the end. At the end, we want to find the density, right? The density is the mass divided by the volume. So to calculate the density, I need to know the mass of the gas and its volume. Well, all I have is a pressure and a temperature. They didn't tell me how much gas. We can pick the amount of gas because the density is going to be the same. So let's choose something that makes our lives easier. We're going to choose to look at 1 mole of gas. What's the mass of 1 mole of xenon gas? One mole of gas, we're going to use the molar mass from the periodic table. Xenon is 131.3. So the mass of 1 mole is 131.3 grams. That's my mass. Okay. The other thing I need is the volume. I've got a pressure and a temperature, and I picked 1 mole, so that's my N. N equals 1 mole. I could use the ideal gas law to calculate the volume, right? They're giving us the wrong unit because these are the units that are commonly used for measuring these things. Like a barometer, you're not usually going to see it register in atmospheres. You're usually going to see millimeters of mercury or even inches of mercury. A thermometer, I've never actually seen a thermometer that is labeled in kelvins. It's always in Celsius, because we can't even get to 0 Kelvin, and so most of the thermometer wouldn't be used anyway. So we're almost always going to have to convert these guys. Okay. So here I've got my equation kind of in the middle of nowhere. So I'm going to come down here. The volume is equal to the amount of gas in moles. And we chose 1 mole. We can choose exactly 1 mole. So that's not going to limit our sig figs. And then we have to multiply by R. And then by the temperature. Oops, 318. It is really easy to write these numbers down and leave digits out, swap digits, move the decimal point. So, like on a worksheet or homework where you get instant feedback and it says, no, that answer's wrong, and you're like, I'm sure I did it right. Go back and make sure that you copied the numbers from the problem correctly. Okay, it was 742. I wrote 742 instead of, maybe you wrote 724. Well, that'll get you the wrong answer. Make sure that you take this converted number and you put it into the calculation correctly without messing up your digits. So again, we're going to have a bunch of units canceling out. So we'll end up with a volume in liters. 0.08206 times 318 divided by 0.97. 632. 26.728 liters. Oops, that's not what I wanted. There's just my volume that I need to put into my density equation. So the density is the mass, you get that right here, divided by the volume. Three sig phase, 0.491 grams per liter. Any questions? Yes.
So when the amount isn't mentioned, we can just assume it's 1 mole?
Right. If the amount isn't given, you can pick whatever size you want.
It'll be the same?
It'll be the same. Because the density of something does not change with its size. It's an intensive property. For a gas, it'll change with its temperature. It'll change with the pressure. But if you have more gas under the same conditions, the density is the same. And that kind of bothers people. It's like, well, it seems like you're just like cheating to say, well, let's just choose 1 mole. But it doesn't matter what the size is, so we might as well make it easier on ourselves, right? You could choose 15.3 moles if you wanted to. You'd still get the same answer. Any other questions? There's a lot of pieces in here, right? There's converting units. We learned how to do that. There's using the ideal gas law to calculate the volume. That's something we just learned how to do today. There's this idea of what is density, mass divided by volume. You're also having to do a conversion with a molar mass here. So lots of little pieces, and most students will struggle with putting them all together. And so try to take a step back and look at the big picture of what you're doing. Maybe even write some notes to yourself before you start in with the calculating, because once you get into all these numbers, you're like, you find an answer and you're like, wait, why was I doing that? What was I trying to find at the end? Ever happened to you? Yeah, it happens to me in class occasionally, and it's embarrassing. But, for this one, you could say, well, what is density? So mass divided by the volume. Okay, I need to find the mass, I need to find the volume. How am I going to find the mass? Well, it doesn't give me an amount. I'm going to choose an amount that's easy, 1 mole. So I need to find the mass of 1 mole, and then I need to find the volume of 1 mole and plug those into the equation. Little notes to yourself. Okay. 4.91 grams per liter. Yes?
So if there was a question just like that, but set at STP, we can just use the 22.4 instead of trying to find the volume?
Yes, if it's at STP, you can use 22.4 liters per mole, and that makes finding the volume really easy. Yep. Anytime you see at STP in a problem, you should think, oh, I can probably use 22.4. Okay, there's a couple of questions on the worksheet, and there's a heading that says molar volume of a gas, right? So for those problems, they are at STP, and the calculations are much simpler if you use 22.4 liters per mole. You can do it the hard way, but I'd like you to use the molar volume when you can. Okay, so this one is a little bit different. We're given the density of a gas. The density of a gas is 1.43 grams per liter at a temperature of 23 degrees Celsius and a pressure of 0.789 atmospheres. Calculate the molar mass of the gas. So it's a little bit like the previous problem in reverse, but then again, not quite. Highlight the numbers. Highlight what we're trying to find. Pull the numbers out. This is a per unit, grams per liter. It's written with a slash here because that's easier to type. But then a lot of us, our brains don't recognize that that's a fraction. So when you write this with your hand, you want to make sure that you show it as a vertical fraction. We've got 25 degrees Celsius, and we've got 0.789 atmospheres. So we could label these things. This is the density, this is the temperature, and this is the pressure.
It's 23 degrees.
23, thank you. Well, molar mass. It's probably not obvious what we should do. Well, what is molar mass? The molar mass equals the mass in grams divided by the number of moles, right? Does the molar mass, that's a tooth. Does the molar mass change if you have more or less of a sample of an element or something? No. The molar mass of helium is always 4 grams, whether you have a tiny bit or a whole bunch. The molar mass is the same. So this is another time when we can choose the amount, because it doesn't matter. So what's easiest? Choose 1 mole. Okay. Actually, choosing 1 mole is not the easiest here. We need the mass in grams, but we're trying to calculate the molar mass. So if we have a mole here, we're not going to be able to calculate grams, are we? We got this density. This is the mass of 1 liter. Maybe we should choose 1 liter of gas instead. So let's choose a volume. We'll choose 1 liter to be our volume. So then, if we're looking for the mass in grams of 1 liter, the mass in grams would be 1 liter. We're going to use the density and we can calculate the mass. 1.43 grams. So that's the grams. The other thing we need is moles. Well, we've got temperature and pressure, and we picked a volume. Volume equals 1 liter. R is R. How can we calculate the number of moles? Ideal gas law. PV equals nRT. nRT. So this time I'm solving for N, moles. So I'm going to divide both sides by R and T. The moles is going to be equal to the pressure times the volume divided by R times the temperature. Well, do we have all the correct units? We've got liters, which is good, and atmospheres, but again, the temperature's not right. We need to convert to Kelvin. They're having too much fun over there. He gets a little worked up sometimes. Okay, so now we've got all the right units. So the pressure was given to us, and the volume is something we picked. And then we're dividing by R. Times the temperature. I am dividing by two things that are themselves multiplied. It's very easy to get the wrong answer on your calculator. A lot of calculators have a function where you can enter things as a fraction. And so up here you could type, you could type 0.987 times 1, and in the denominator you can type 0.08206 times 296, and it'll do that for you. That's fine. Go ahead and do that. If your calculator does not do that, everybody wants to multiply here. If you're going to do that, you have to put parentheses around the bottom. Otherwise, you're going to end up taking, you'll be off by a factor of 296 squared, which would not be good. So on my calculator, 0.789 divided by, open the parentheses, 0.08206 times 296, close the parentheses, 0.032483. And then I'm like, what was I calculating again? Oh, atmospheres cancel and liters cancel and Kelvin cancels. Oh yeah, it was moles. Okay. Make sure that you can get your calculator to show you that answer. Okay, so this is the amount of gas in moles, which is what we need in our denominator. So the molar mass equals the mass in grams, which was the 1.43 grams, divided by the amount in moles, and the units there are grams per mole. So the molar mass is 44.0 grams per mole. Is that a reasonable molar mass for a gas? Like, I don't know. Well, let's think of some unreasonable molar masses. How about negative 15? No, that's ridiculous, right? You can't be negative. How about 0.02 grams per mole? Why doesn't that work? That's smaller than hydrogen. You can't have anything smaller than hydrogen. So the lowest you're going to have would be hydrogen atoms, which would be 1 gram per mole. What do you have 50 gazillion grams per mole? Yeah, that's probably not right either. So here we've got a positive number. It's bigger than 1. It's not ginormous. That's reasonable. The most common thing that happens here is people will end up with a positive mass, but it's much smaller than 1. And that means you divided wrong or multiplied wrong. There was some math thing you did wrong. Any questions? Yeah, I don't want to do all that. Let's just do this one and call it a day. Arrange the following gases in order of increasing density at STP. This is a great exam question. So how do we even think about this? So this is at STP. So if we have equal moles, we have equal volumes, right? And then what is density? Density is the mass divided by the volume. So we could say, well, if we had 1 mole of each of these gases, they would all have the same volume, right? 1 mole would be 22.4 liters at STP. How do we figure out which one has the largest mass? The molar mass, right? We've got neon, O2, F2, and Cl2. Which one has the largest molar mass? I think it's going to be the chlorine. Neon is 20. The chlorine is going to be 35 times 2, right? So chlorine is the largest mass. Is that going to be the biggest density or the smallest density? It has the largest mass. Biggest density or smallest density? The biggest density. The most dense. Yeah. That didn't work very well, did it? So what I'm thinking of here, I'm thinking of 1 mole of each gas. That means the volumes are equal. In fact, 1 mole would be 22.4 liters, right? All the volumes are the same in my imaginary 1 mole samples, but the masses of them are different. The mass of Cl2 is larger than all the others. If I have my density equal to a larger mass divided by the same volume, I'm going to have the highest density, right? And so which one's going to have the smallest density? The one with the smallest molar mass, right? Which would be neon? Oops, get right up there. Because 1 mole of neon weighs 20 grams. 1 mole of O would be 16, but this is O2, so it's 32 grams. F2 is 19 times 2, right? So the neon is the lightest. And then the next heaviest is the oxygen, and then the fluorine, and then the chlorine. When it wants you to arrange things in an order, I think it's best to not look at the choices, because they're confusing. Figure it out yourself, and then find out which option matches what you came up with. A common problem that happens here is that students will choose the exact opposite of the correct answer. It actually takes skill to do that. Skill and a simple misunderstanding. So, order of increasing. I've become convinced that they don't teach you about that in the public school system, because I find most students that just, I don't know, just doesn't really mean much to you. Well, what does it mean? You need to know, because there's going to be questions like this. Order of increasing means the smallest thing is first, and they get bigger and bigger and bigger and bigger, right? And the biggest thing is at the end. Order of decreasing, you start with the biggest one and you go down to the smallest one. Sometimes it will show you these greater than or less than signs, and sometimes it'll just be a list. So there's also some confusion about greater than and less than and what those exactly mean. This is how I think of it. This side of the symbol is small, and this side of the symbol is big, right? So we got the big number on this side and the small number on that side. Here, the left side is big, it's open, right? That's the big side, and here is the tiny pointy side, so that's small. So this symbol here is telling me that the density of chlorine is greater than the density of fluorine. So then what's my answer? It's going to be A, right? Wait a minute, you took us all over the place, and this is our answer, but it's a multiple choice question. We have to figure out which of these matches, right? Any questions? Yeah, we'll do that next week.